Hi everyone, so today we're going to talk about chemical equilibrium. That's chapter 8 of our Heinemann chemistry textbook. So let's start by talking about this particular process here. This is called the Haber process. It's the process in which ammonia is produced by adding nitrogen and hydrogen gases in a chamber. So what we've got now, this is the reaction up here, the complete reaction, and what we've got in our vessel is 1 mole of nitrogen and 3 moles of hydrogen gas. So what do you think is going to happen? You know, it's in a container and the temperature is 400 degrees Celsius for the reaction to take place. So immediately you would think, well, after a while, when the reaction is complete, we're going to have 2 moles of ammonia gas in the container. However, that's actually not going to be the case. No matter how long you sit there and wait and wait and wait, you will get to a point where not only do you not get 2 moles of ammonia, you will only get 0.6 moles of ammonia, and that concentration remains constant. And so does the concentration of nitrogen and hydrogen. All these three will remain the same concentration inside this container, no matter how long you wait. Now, if you think about it, this reaction of nitrogen and hydrogen reacting together to form ammonia is reversible. I mean, what is stopping the ammonia from breaking up into the constituent nitrogen and hydrogen gases? There's nothing really stopping it. So this leads us to the concept of equilibria. And this arrow here, which you would have seen before when we talked about electrochemical series, the equations of electrochemical series, you would have seen this double arrow, which means the forward and backward reaction can both take place. Now, let me demonstrate this concept of equilibrium to you in this example coming up. Actually, sorry, before the example, let's have a look at this diagram. Okay, so if we have enough activation energy, okay, for the forward reaction to take place. Now there's also probably enough activation energy for the backward reaction to take place. So forward and backward reaction can take place, providing that there is enough activation energy and the correct orientation of collision to drive it to do so. So we're having a forward and backward reaction, okay? Now, we've always assumed that reactions always go into completion, but in this particular topic, we'll see and understand that that's not the case. And here is the demonstration for it. So here we have a container. This is going to represent our reactant. So we have this much reactant and the reaction hasn't started, so we've got no products at the moment. Now, I'm going to demonstrate to you how reactants is going to form products by scooping out the water from reactants and putting into products. So I have 2 different sized scoops here, measuring cups, things. And what I'm going to do is show you the reaction proceeding forward. Now, reaction proceeds forward, so our reactants form products. Now, as I said before, what's stopping the products from going back and forming reactants? So I'm going to continuously do this. I'm going to put the reactants are going to form products. Some of the products are going to go back and form reactants, and reactants will form products, and so forth. So just bear with me while I show you this example. So it keeps going. I'm filling each of the scoops as best as I can. And it continues, and it continues. Now, what do you notice after a while? What you would notice after some time, as I continue to do this, that the amount of product and the amount of reactant remains unchanged. I don't have all of my reactants in products, and I don't have all my products as reactants. And if you have a look at this, if I scoop this out and I fill this up, I'm actually filling 1 full little cup of my products. So what I'm doing basically at the end, as I'm continuously scooping it in and out, is that we've reached a point where we have a dynamic equilibrium. What do we mean by that? The forward reaction is equal to the backward reaction. So as the reactants are forming products, the same amount of products are forming back into reactants. So we have reached a state of equilibrium. Equilibrium doesn't mean we have equal amounts of reactants to products. what equilibrium actually means is that the forward and backward reaction is occurring at the same rate, such that you don't actually see any difference in the amount of reactants and products when a system has established that equilibrium. Now, as you can see here, we do have more products than we do have reactants. And in saying that, we can say that in this reaction, the forward reaction is favored. So the reaction that proceeds from reactants to product is more favorable than the reaction going from products through to reactants. Now, this might not always be the case. I mean, what if I was, and I probably won't demonstrate it to you, but what if I was to, switch the scoops over, the large scoop being here and the small scoop being there? What you're going to get is that you're always going to get a lot more reactants than you would products, because you have a lot more products going back in to the reactants per unit of time. So if that was the case, if we end up having more reactants than we have products after equilibrium established, then we have an equilibrium system that favors the backwards reaction going the other way. But I'll talk about that a little bit more later. So we've always assumed that reactions that take place always proceed to completion. So by completion, we say that all the reactants convert to products, but in actual fact, most of the time that's not always the case. Now, rather than completely forming products, they reach a state of equilibrium, as you saw before in the demonstration. So what's actually happening is that the collision between the product particles can result in reactants being formed. So the backward reaction, we call it, is taking place as well as the forwards reaction. And they eventually get to a point where the rate of the forward and backward reaction is exactly the same, and therefore we call it the dynamic equilibrium. The word dynamic means it's still constantly moving. Okay, the reactions are still, it looks like nothing's happening. However, the reactions are still taking place, but you can't detect it because the rate of the forward and the backward reactions are equal, so that you don't actually detect any differences in concentration or amount or quantity if you were to detect it. Okay, so here is another example. So hydrogen bromide over a period of time. So hydrogen bromide is a reaction that over time will decompose, okay, into hydrogen and bromine. Okay, so this is an example, a sample reaction that will proceed to completion. However, if we were to do one for the concentration of hydrogen iodide over a period of time, it's not actually going to go to completion. It'll get to a point, so where this curve flattens, the concentration of hydrogen iodide is exactly the same. And this is how we know that we've reached a state of equilibrium, because this quantity doesn't change. Doesn't mean there's no reaction happening. It does not mean that at all. It just basically means that the forward and backwards reaction is going at the same rate. So when we're talking about equilibrium, we're talking about reversible reactions. Now, they have a dynamic nature, and we're going to use this double arrow to show it. Now, at equilibrium, as I said before, the reaction doesn't stop, but it just looks like it has, because the amounts and concentrations remain the same, but it's in a dynamic state. The forward and backwards reaction proceed at the same rate. Now, an important point to note is that catalysts have no effect on the position of the equilibrium. So in that demo that you saw before with the water being, poured into or scooped into the other container and backwards and forwards, if there was a catalyst, you can just imagine me scooping a lot faster. So if there was a catalyst that is speeding up this reaction, you'd see it reach equilibrium faster than you saw before. However, the position doesn't change. Now, what do we mean by position? It means that before, what you saw is that you saw a lot more products at the end than you did reactants. So we're still going to get a lot of products and not as much reactants, but that is going to be maintained. It's going to be established. The speed at which we reach equilibrium just happens a lot faster. It only increases the rate in which equilibrium is established. So how quickly do we reach equilibrium? But it doesn't have any effect on the equilibrium's position. So let's have a look at these examples over here. Okay, so this top reaction in the blue is the Haber process, and this reaction in the pink dotted line is the Haber process in reverse. So basically we're breaking down ammonia to get our gases. Now the point where both curves meet and become flat, as you can see here, where the concentration, where the rate is actually the same, sorry, not concentration, so where the rate of the forward and the backward reaction meets, that is when equilibrium is established. The point where they meet, and they continue to be that way, is the point where the equilibrium is first established. Now this is a rate versus time graph. On the other side, we have a concentration versus time. So it's a little bit different. They don't meet, okay, and continue along the same plateau. What you actually see is, if you think about it, we start off with hydrogen gas and hydrogen gas and nitrogen gas. So as time goes by, the hydrogen reacts with nitrogen. So the concentration of hydrogen and nitrogen will start to decrease. Would you agree? And because they're forming ammonia, and the ammonia curve starts to increase because hydrogen and nitrogen are being used and we're getting ammonia. And this will continue, but it will get to the point where the amount or the concentration of hydrogen remains constant, and so does nitrogen, and we see no more additional ammonia being formed. So this point here, where all three lines plateau, is the indication, because all the concentrations are the same, is the indication when equilibrium is established at this time point here. Here's another example demonstrating equilibrium. So we've got dinitrogen tetroxide, so N2O4 gas, and we leave it in the chamber, and after 3 seconds, it decomposes to form nitrogen dioxide. And that is a gas that has color. Now over time, so another few more seconds go by, and you'll get this color here. Now, no matter how long you wait after this 8-second mark, the color doesn't change. It doesn't get darker because we're not going to get more of this forming, we're not getting more reactants forming products. And we're also getting the same amount of products forming reactants going back the other. So in the red at the two reds at the end, we've reached an equilibrium. It doesn't mean that we've got all nitrogen dioxide. We've actually got a mixture, but it will not proceed forward anymore, nor will it proceed backwards anymore. The forward and backward reaction will remain constant from this point on, unless we change the conditions somehow, and therefore we've reached what we call an equilibrium. Now, rate and extent are two words I need you to understand. They're actually very different things. You obviously understand rate from yesterday's rate lesson. Now, rate describes how quickly something happens, whereas the extent is how far forwards the reaction proceeds. Now, if the reaction proceeds all the way to the end, then we can say that we basically have 100% product and no reactants, because everything's to completion. So that extent of reaction is 100% complete. However, as you saw in the demonstration before with the scooping of the water, it gets to the point where the amount of reactants and products remain, they're not equal, but they remain the same. So we have a lot more products than we do reactants, but we still have reactants that will never all completely form products because of the way the reaction is taking place backwards and forwards as well. So extent is talking about how far forwards the reaction is taking place. Some reactions don't actually go very far forward, so you end up, no matter how long you wait, just like in the Haber process, in those conditions, no matter how long you wait, you're only going to get 0.6 mole of ammonia from 3 moles of hydrogen and 1 mole of nitrogen gas. So extent is how much product we form. And the thing is, the extent of the equilibrium, you don't know how long it will take for an equilibrium to establish. We don't know how fast it's going to get. It might take several years before we establish equilibrium because the reaction rates are that slow. Or as you saw in the example before, this only takes a few seconds and we've established equilibrium. So extent and rate are two completely different things. We can't infer one from the other. And that leads us to something called the equilibrium constant. So when we're talking about the extent of a reaction, so how far forward does a reaction go, we can calculate that mathematically using Kc, also known as our equilibrium constant. So how do we do this? So have a look at this reaction here. Now, the lowercase letters represents the number of moles of each of the molecules that are there, or in the capitals is the actual substance itself. So we have little a molecules of big A, little b molecules of big B, that's forming C and D as well. So to calculate equilibrium constant or Kc value, we multiply. So firstly, we get the concentration of our products multiplied, raised to the power of the number of moles of that product, multiplied with, okay, let me say that again. So basically, the concentration of C raised to the number of moles of C multiplied by the concentration of D raised to the number of moles of D. Okay, so we're basically, so even if there was just only one product or, 3 products, we'll have to write their concentrations down, raise it to the power of their moles according to the reaction, okay? And then we divide it by the concentration of A raised to the power of the number of moles of A multiplied by the concentration of B raised to the number of power of moles of B. And I'll show you some examples in a moment, but let's have a look at how to interpret Kc value. Actually, no, should we? Okay, let's do that. So remember this, and let's go back to this example here to determine the equilibrium constant of this reaction. So we've got our equation here, we've got the concentration that's at equilibrium, and we're going to calculate the Kc value for this reaction over here. Now, Kc is given by the concentration of the products raised to the power of the number of moles. So for this particular one, it's raised to the power of 2. And if there was another product there, we'd also multiply it with the concentration of the product raised to the number of moles of that product as well. So that will be over the concentration of the reactant, so concentration of N2, and in this case it's raised to the power of 1 because the coefficient is 1, so we don't have to do anything, multiplied by the concentration of hydrogen gas raised to the power of 3 because it says 3 up here. So if we plug all those numbers in, Kc would equal to 0.6 moles. We're using the values at equilibrium. That's going to be raised to the power of 2 over 0.7 multiplied by 2.1 raised to the power of 3. Now that is going to give us a Kc value of 0.0, well, to one significant figure, guys, is going to be 0.6. Okay. Now, what does it actually mean? Let's remember that 0.06. So Kc value, or the equilibrium constant, talks about the extent of the reaction. Now, we had a Kc value of 0.06 before, and if you have a look at how we interpret Kc, if Kc value is greater than 10 to the negative, 10 to the power of 4, then we get a significant conversion of reactants to products, okay? And if we get something like this, we've got where Kc is actually a value less than 10 to the negative 4, then we can say that not much conversion has occurred. Now, in the top case here, we're saying that the equilibrium lies, or the extent of the reaction lies to the right of the equation. So there is more products favored. In this example here, or in this, if you get values in this range, we're saying that the reaction favors the backwards reaction, and we don't actually have much conversion of the reactants into the products. So if it favors the backwards reaction, we're saying that the equilibrium lies to the left. And if we get any value in between, then we say that the equilibrium doesn't favor either side of the reaction at all. Okay, so there's no favoritism going forwards or backwards. You probably get a very good mixture of the products and the reactants. Now, an important point to note that for a particular reaction, the chemical equilibrium, or the equilibrium constant, is the same at that particular fixed temperature. Now, as soon as you change the temperature, Kc value will also change as well. So don't think that, for the Haber process that you saw before, that 0.06 is going to be the equilibrium constant for all Haber processes. The moment that we change the temperature from 400 degrees, if we increase it or if we decrease it, we're going to change the extent of our reaction. Okay. Now, one thing that I forgot to mention is that the unit for equilibrium constants, we actually do put a unit down, but it has no real meaning. So I'm going to show you what I mean by that. Now, going back to this example here, the thing I've forgotten to note down was the unit. I'm so sorry. So here, these units should be in concentrations, right? So here, concentration or molar. So up here, it would be M, and M is to the power of 2. And down here would be, now nitrogen gas is M multiplied by hydrogen gas, which is concentration to the power of 3. So we actually have M2 over M4. That gives us 1 over M2. And if you remember how to, sorry guys, this can be written as M to the power of -2. Okay, I hope you paid attention when you were taught indices in maths. So the unit for this particular example here is going to be M to the -2. Now the units for each reaction is going to be different. They don't really mean anything, but you have to have them there. Now it is possible also that you might not have any units. So if the units, when in that unit calculation all cancels out, then you end up with no units at all. Okay, so, but you have to have it there because VCAR, your exams, your SACs, you have to write the correct unit. Now we have another quotient here. We call it the reaction quotient QC. It talks about the extent of the reaction at a particular point in time. So while KC talks about the extent of the reaction at equilibrium, QC talks about the extent of reaction at a particular point. So if you think about what we did in that example with the water before, we can say that the Q was a lot higher than, sorry, let's not talk about that reaction. Let's just talk about this QC value here. So something to keep in mind is that if the QC value is lower than the extent of the reaction at equilibrium, then we're saying that the reaction forms more products at that particular point in time. If your reaction quotient is greater than the K value, if it was at equilibrium, then we're saying that the reactions form more reactants. And if they're both equal, we're saying that the reaction is at equilibrium. Okay, so this is just something to remember. The QC, if it's smaller, what does it mean? If it's bigger than the K, what does it mean? And if they're equal, what does it mean? If you can remember that, you should be okay for your exams. So here are a few examples. I want you to write the following expressions for each of the equations below. So I want you to write equilibrium expressions for each one. So what do I mean by that? You're basically just filling out this. So the concentration of blah blah raised to the power of blah blah. So for this one here, I'll upload the solutions shortly. And over here, can you, well, you can, I guess, do this in your own time. There's no calculations involved here because you haven't been given the concentrations, but I want you to learn how to write the set up the KC equation. And then over here, now, can you work out, or can you tell me whether the forwards or backwards reaction is more favored? So have a look here. This is, that's the reaction that's meant to be a plus, I presume, or an arrow. No, it's meant to be an arrow. Okay, so water breaking up to H3O to OH minus, and the K value is 3.2 times 10 to the negative 18. What does this actually mean? Okay, it means that we're not actually getting very much products. We're actually having more, we actually have more reactants because the reaction doesn't proceed very far left, very far right. So it actually remains to the left a lot more. For B here, 3.8 times 10 to the negative 9, once again, it's another reaction where the backward reaction is more favored. So the extent is not very far forwards at all. Over here, this is ammonia breaking down into the two constituent gases at 475 degrees, and that's meant to be, sorry guys, 3.8 times 10 to the power of 5. This indicates that the forward reaction is more favored. And D, with the K value of 145 at 40 degrees Celsius. So notice that each of these have a temperature next to it, because the moment we change the temperature, we also change the position of the equilibrium. So K being 145 means that we're going to get that like neither forward or the backward reaction is favored. Okay, and that's pretty much all I need you to do for today.